Okay, well, thank you all for coming to this talk, which is named Uncovering SAP Vulnerabilities. And it's basically the process I follow trying to understand how the protocol works and trying to use that information from a security perspective. So I'm Martin Gacho from the consulting team of Core Security. So let's start by reviewing the agenda for the talk. First, I will give a quick introduction on the topic and what SAP is. Then I will start showing some of the previous work that has been done on the protocol and showing the motivation for my research. And then I will show some of the main components of the SAP NetWeaver architecture for those who are not familiar with. And moving on to the main section of this talk, which is dissecting and trying to understand how the protocol works, ending up with some results, showing some of the tools I developed, and discussing some defenses and countermeasures that can be applied. So let's start. SAP is a software company based in Germany. It's the leader business software provider. And most of the large enterprises runs the most critical process on subsystems. So it has become a hot topic in security in recent years. And I think that some components are still not well covered. One of the things is that some of these protocols are proprietary and documentation is not public. So this is one of the things that makes it difficult to have more knowledge about cybersecurity. So this talk is basically about the Diag protocol. Diag means Dynamic Information and Action Gateway, and it's a network protocol used for communications between the SAP GUI, the desktop client application, and the application servers, the SAP NetWeaver application servers. So this protocol is present in every SAP NetWeaver installation that is based on ABAP. And one of the main characteristics is that the protocol is not encrypted and it's only compressed by default. So encryption is optional and can be implemented using a third-party product or a free product that were released by SAP last year. And the component is called SNMC for Secure Network Connections. So the protocol runs on TCP ports 22,000 and 2299. And there were a lot of work in the recent years around the protocol. Back in 2009, there were some proprietary tools to trying to dissect the traffic of the protocol and getting clear text credentials, but these tools were not public, so there's no much. In 2009, Securon published a paper in which he introduced a method for sniffing the clear text credentials, which they called a reflection method, which is basically to get a network trace of a login and starting a fake server and using the trace of that session and connecting with another GUI to that fake server and look into process memory to get the plain text password. So it's not a very useful attack. It works, but it can be used in a practical way. So in 2010, Denis Yurichev published in his blog an article where he found that the compression algorithm being used in the protocol is the same that the compression algorithm using in MaxDB open source product. So MaxDB is an open source database. So the implementation of the algorithm, the compression algorithm, is available, and he writes a small tool to decompress the traffic, and it helps a lot trying to understand how the protocol works. More recently, in 2011, there was a lot of work on the protocol. The main one and the most interesting is a proxy-like tool that was released by Zenpost, and it's a hub application that you can run to make a proxy, to proxy communications between a GUI and the application server. So additionally, the compression plugin for Warshak was also released, and some sniffing capabilities were added to Cain and Abel to get also credentials. So as can be seen, most of the previous work was based on compression and decompression of the traffic, and the protocol inner workings and details about the packet formats remains still unknown. And there's no practical tool to perform a penetration test against this protocol or to make an assessment. So this was mainly the motivation for my research. And also the protocol is relevant because it's present in every NetWeaver installation. And we often see customers that are not using encryption. So this makes also an interesting point. And additionally, out of the around of 2,200 security fixes published by SAP, only 2 affects the protocol. So this also makes an interesting point to make some assessment and trying to attack the protocol. So let's move on to main components of the SAP NetWeaver architecture. The NetWeaver architecture is the infrastructure layer where all SAP's applications runs, and it's based on a 3-tier layer. So in the presentation layer, there is the SAP GUI client, which is a FAT client, a desktop application, and a browser in case you are accessing SAP's web applications. The database layer is independent, so you can use any commercial database product. And in the business layer, there are 2 main different versions of NetWeaver. One based on Java, and the other one based on ABAP. And we will be talking on ABAP in a few slides. So this talk is mostly focused on the ABAP engine part and the SAP GUI client, which are the components that uses the protocol for the communications. So some concepts and components that I want to mention because are relevant. The first one is the ABAP. ABAP is SAP's programming language. All standard programs, almost all standard programs of any SAP application are written in this language. And you can also customize and create your own programs. So this component plays a key part on every SAP system. Another interesting concept is the dispatcher and the work processes. Dispatcher is the service that listens to the network for requests coming from the GUI application, from the GUI client, and distributes all those requests to a pool of different work processes. Each work process handles different tasks and runs different tasks. There are 5 different work processes. We will be mostly focusing on dialog work processes, which are the operating system process that parses all the requests coming from the Diag protocol. And the last concept that I want to mention is the dialog processing, which is the programming method which is used for all the ABAP programs, and is based on 2 different concepts. Screens, that are all the screens that you see in the SAP GUI client, with all the controls and input boxes, etc. And the dialog steps, which are all the logic behind one screen and another. So this is important for the protocol because all the screens travels from the network, from the GUI to the server, and from the server to the GUI in the Diag protocol, using the Diag protocol. So SAP uses different network protocols at different components. Some of them are standard, like HTTP, SSL, so etc., and others are proprietary protocols. The first, and one of the first protocols that came up is the network interface protocol. It's a protocol used to do some error handling and do some checks on all network connections. And different proprietary protocols runs above this one. So you have, for example, the RFC protocol, which is remote function call, and it's used to call a remote module in another system. The router protocol, which is used by SAP router, that is an application level gateway that is used to control access between different network segments to SAP systems. Then you have the Diag protocol, which is the subject of this talk. So having said that, setting some context about SAP, let's start by reviewing the process I follow trying to understand how the protocol works. So my approach was mostly a black box approach. One of my goals was not to reverse engineer the binaries. The binaries are very huge and the code is really complex. So the idea was mostly to enable traces at both sides in the GUI and the application servers. And by analyzing network traces and the application traces, trying to understand how the protocol works and how all the packets are composed. So another of the goals was to learn by interacting with the different components, and at the time that having some knowledge about the protocol, implemented in my own tools. So let's see how a regular Diag packet looks like. First is the network interface protocol, which is only a 4 bytes header that it contains the length of the remaining payload. And the Diag protocol is composed by different headers and the payload itself. There's one header that is optional and it's only used during the initialization, which is the DP header. Then you have the Diag header, which carries information about the communication. The compression header, which is also optional and only present when the payload is compressed. And the payload itself, that is the part that carries all the relevant information, all the screens data, and etc. And it's composed by a variable number of different items. So let's start with each one. Initialization is started by the GUI application. It's only composed by the first packet and only travels and compress. And during my test, I only identified 2 relevant states of the protocol, when the connection is initialized or not initialized. So there's nothing more on this. The DP header is a 200 byte length header, and it has 2 different semantics. For an internal perspective, it's used for inter-process communications between the dispatcher service and all the different work processes. And from a network perspective, which is the relevant for this talk, most of the fields are filled with default values. and there are only two relevant fields, a terminal name and a length field, which is the length of the remain of the packet. So let's move on the Diag header. The Diag header is present in all the Diag packets, and it's an 8-byte length header. There are only two relevant fields. The first one is the mode. The mode is a 1-byte field that identifies different sessions using the same communication channel. So you can, for example, have two different SAP GUI clients running different transactions, business transactions or programs in SAP, and these fields identifies each one. The remaining relevant field is the compression flag, which is set to a different value when the compression is enabled or disabled, and when encryption is being used with SNMC. So about the compression, well, it's enabled by default. It uses two different variants of the length compression algorithm, LS77 and LS78, and it's the same implementation of MaxDB open source products. So this code is available. And one interesting thing is that can be disabled in the GUI application by setting a special environment value. So when the payload is compressed, there's a compression header with 4 fields. It's also an 8-byte length header. The first one is the uncompressed length of the payload, an identifier of which algorithm is being used, a magic bytes, which are constants, and a special field which depends on which protocol is being used. So the payload itself, which is the most important part of every packet, is composed by a variable number of items. During my test, I identified these 11 different items. Some of them are for care information about the screen, about the connection, XML streams, and etc. And we will be focusing on one of these items, which is the APPL or APPL4 items, which carries the most relevant information. So each one of these items has also their own header. The first field is the type, which denotes if there is an APPL or APPL4 item. Then you have a length field, which also can be 2 bytes length or 4 bytes. And then you have 2 additional identifiers, an ID and SID. During my test, I identified 172 different combinations of IDs on SIDs. So if you look at a Diag packet, you can find several different items and several different APPL items, each one with their own mean and their own format. So the combination is really big, and the complexity of each packet it's also interesting. So there are some highlights or some things that I found interesting during my research. The first one is that one of the APPL items that must be included during the initialization is the protocol version. So one of the things that I found is that if you specify a specific version number during the initialization, all the remaining packets coming from the server will be uncompressed. So this is useful, for example, if you are writing an exploit or some script or some code, and you don't want to use all the compression functions in all your packets. Another interesting thing is about the authentication. What I found is that the authentication is performed as a regular dialog step. So the authentication is, from the protocol perspective, is the same that every single transaction that you can run in the GUI application. There are input boxes, you enter information, that information travels to the server parses it and handles it, and that's all. So this has also an interesting thing from a security perspective, and is that all the packets and all the requests coming from the GUI application using the Diag protocol are handled using high privileges, because the program doesn't know which are the user, and it's not already authenticated. So another thing that I found interesting, and I think that is the most important one, is that I found that the Diag protocol is used only for carrying all the screens and all the context information, but the actual actions on both sides, on the GUI application and on the application server, are performed using RFC codes. So there's one special APPL item that carries RFC codes. RFC is another SAP's proprietary protocol. It's mostly used for interfaces and for communicate different SAP systems or SAP with external systems. So this is interesting because the server does not accept RFC codes until you have authenticated, but because of the protocol is unencrypted and there's no strong or mutual authentication, the client do accept RFC codes, and this can be used in a very interesting way. So let's move on to some results and finding of my research. First is for packet dissection. I wrote a Warshak plugin. It's a plugin written in C and C++, and it has 4 main dissectors. The first one is for the network interface protocol, and it does all the DCP reassembling, basically not much. I also include an additional dissector for the router protocol with some basic support. And then there's the Diag protocol dissector, the most important one, which handles all the decompression and identifies the different parts of the DP header, the Diag header, and the compression header. It also identifies the different items, and some of the most relevant are also dissected. The value of those items are also dissected. And this dissector also calls the RFC dissector when found an embed code. So the last dissector is for the RFC protocol. It has some basic coverage because it's another protocol, and they will need another research project. But some of the relevant parts of an RFC code are also dissected. So here are some screenshots. I will be showing some fun with the tool later. For packet crafting, I built a small library using Scapy. Scapy is a Python library to craft packets at a low level. It's a framework that you can use to build your own protocol implementation. You can extend and create new packets using Scapy classes. So there are 4 main classes: the SAP network interface class, another class for the Diag DP header, the main one for the Diag protocol, which is the one that handles all the compression, one class for Diag items, some custom classes are included for the relevant items, but you can also create different classes for the different items. So the tool also includes an extension for all the compression and decompression, which is based on the compression functions being public. So I also include some example scripts and proof of concept scripts, for example, to gather information on the application server, to perform a login brute force using the protocol, to run a man-in-the-middle attack, set a proxy between the GUI and application server, or to plant a fake Diag server. So I will show some of the tools working. So the setup for these demos is very basic. Yeah. I have this Linux box with my tools installed, and I have an application server running in another VM. So I will start the Wireshark, and using the SAP GUI for Java, make a connection to the application server. Okay, this is the standard SAP GUI desktop application. So I will make a login, and just to look how the packets looks like, use the display filter, and this is the initialization packet sent from the GUI to the application server, and you can find the GP header with all the relevant fields, the Diag header, and the message which each item and their values. So, for example, if you want to find the credentials, you can use the different filters and look, for example, to one of the text contract that has a flag, which is the invisible flag, denotes that there's a password. And looking into the packet, you can find, for example, the password in plain text. So this is useful for research, for trying to understand how the protocol works. And I will show also how this looks using the SCAPI classes. So I will make a connection to the application server. Connection. And I will grab the login screen, and this is how a packet looks in using the SCAPI tools. So obviously, each of these items and each of these fields can be manipulated, and you can also craft your own packets using these tools. So let's move on how I use these tools. Well, one of my goals was to look if there's any vulnerability in either the GUI client or the application server. So I came up with this fusing approach for the test cases generation and for delivery of the packets. I use my own SCAPI classes. I use WinDBG for monitoring of the target, and I use XML or RFC for synchronization between the different components. And the only thing you have to take into account if you are fusing an application server is that you have to monitor all the work process at the same time, because you don't know which of the work process are handling your request. So using this approach and some manual tests, I found 6 vulnerabilities on the SAP application server. These issues were fixed on May by SAP, and 5 of the issues are denial of servers vulnerabilities. 3 of them requires that you enable the developer traces on the application server, and there are 2 more that does not require that feature to be enabled, but all can be triggered by an authenticated and remote attacker. The another vulnerability, and the most interesting one, is remote code execution when the developer traces are enabled. It's basically a stack buffer overflow while the application server parses one special API item. Well, Francisco Falcon from Course Exploit team wrote the exploit for this issue, so thanks to him. I will show. Well, so all these tools can be used, which I think with 2 different attack scenarios. The first one, and the most obvious one, is to directly target the application servers. For example, to gather information about the servers, to exploit the recently mentioned issues, or to perform a login brute force, or to test for additional vulnerabilities, etc. Another attack scenario that I think is interesting is to target the GUI users. So, for example, you can use all this knowledge and all these tools to perform a kind of client-side attack. There's a feature in the GUI application, which is called GUI shortcuts, that are special .zap files that when you open with the GUI application, the GUI starts a business transaction or a program in the application server. So, for example, you can use this to send by email, or either embedding in a web page different .zap files or GUI shortcuts, point that shortcuts to your own fake servers, for example, to gather credentials or to inject RFC codes in the clients. And another attack scenario is to perform man-in-the-middle attacks to valid GUI users, either by gather credentials or also to inject RFC codes in the user's desktop application. So let's see some of these attacks. First, I will start a netcat here. Sorry. I will launch an exploit for the vulnerability that I found. So here you have a reverse shell. With SAP service account, which is the account that runs all the database services and all the SAP services. And I will show an additional attack vector, which is to set a rogue server, and using the standard GUI connect to that rogue server. For example, in this case, I customized some of the different components of the screen, for example, showing an additional field and customizing the help, the menus. And you can also handle different events started by the GUI. So you can imagine different attack scenarios by planting a rogue server, for example. So there are some defenses or countermeasures that can be applied to try to limit the attack surface. The first one and the most obvious one is to restrict all the network access to the dispatcher service. The dispatcher service run on ports 3200 and 3299 or 98. You can use application level gateways such as the SAP router application level gateway to perform this kind of segmentation. Another and the most important recommendation is to implement encryption on all clients. The SNC component provides both authentication and encryption. It's available for free to, I think, all SAP's customers. Another recommendation is to restrict the use of GUI shortcuts. You can disable this function on all the SAP GUI installations. Another possibility could be to use the web GUI instead of the FAT client. Obviously, patch regularly all your systems to patch especially those affecting the Diag protocol. There are also additional mitigation and countermeasures recommendations in course advisory. And obviously to test regularly all your systems. So let's move on to the end. Well, we have discussed how the protocol packets looks like. The details about the protocol are now available. Practical tools, both for dissecting and for crafting packets, are available. Both tools will be released with the GBL license, so it will be available for anyone. There are new vectors that are now practical. There are well-known vectors, but now it's possible to perform actual attacks. We have also discussed some countermeasures and defenses to try to protect your subsystems. So as you can see, there's a lot of future work that for around this protocol. For example, it will be interesting to perform a security assessment and fusing of all the components and all the different items. As I mentioned, every item has their own format, and there could be different vulnerabilities at the time that both the GUI or the application parses the different items. Also, it will be interesting to have a complete dissection of the RFC calls that are the most important part because of that the actions are performed using RFC calls. Obviously, a full implementation of the different attack scenarios and integration with external tools, for example, exploitation tools like Metasploit, Core Impact, etc. Also, it will be interesting to take a look at how the encryption works and have some coverage for the tools for encrypted traffic. There are different settings that you can apply in the application server, and there are ones that does not provide integrity, for example, so it will be interesting to take a look at the encryption part of the protocol. So that's what's mainly all of the talk. So thank you all.